Okay, thanks to Sean, ex-teacher here, who went through the half cells and how you put them together to make a photovoltaic cell. And he talked about E cell values, and I'm going to take you through now how we can use those to predict reactions. Okay, so what I need to do is make sure I've got my presentation running. We should be good to go. Okay, so let us share the screen now. Okay, so we'll share the PowerPoint screen. There we go. Okay, so I'm going to go through this, and we're going to be looking at how we can predict whether a reaction is feasible or not from E-cell. But we should just try and recap the idea of drawing these cell diagrams, which showing how the setup is. So what I would like you to do is to stop the video, and we're going to need to draw a half cell. And how do you do the standard electrode potential of the manganate 7 Mn2 plus half cell? How do you work out what it is? I'll give you a hint. You might need to think about hydrogen. Okay, so let's have a look at what that looks like. So we have our half cell here, which has got our manganese and Mn2 plus in it. It's got our manganate 7 ions at 1 molar, or 1 mole per decimeter cubed. It's got the Mn2 plus at 1 mole per decimeter cubed. It's got a platinum electrode, because platinum is very unreactive. It's also got acid, and you should be able to remember from our redox equations that this needs to have H plus for it to work. Okay, so the platinum is connected by wire through a voltmeter, so we can measure any voltages that are given out, to our hydrogen electrode. So hydrogen gas is pumped in at 1 atmosphere and 298, so standard conditions. Platinum electrode, again, platinum, very unreactive. And we have acid in here, which is at 1 molar. So that we have H plus at 1 molar, and hydrochloric acid would do. So you have 1 mole per decimeter cube hydrochloric acid. Now, in order for this to be connected, we must have a salt bridge. The salt bridge allows the ions to travel. So through the wire, electrons travel, but through the solutions, it's really important you get this, that through the solutions, it's the ions that travel. So we have a potassium chloride in here, because potassium chloride is very soluble, and the ions will travel up through here. Now, this could be a piece of filter paper soaked in potassium chloride solution, or it could be a glass tube packed with potassium chloride powder. Okay, so let's move on. That's what you should have drawn. So here are our objectives. Look at the standard cell potentials, feasibility, limited limitations of those predictions in terms of kinetic theory and concentration. So it might mean that we can consider thinking about what might happen if we don't have standard conditions of concentration. Okay, so let's have a look. So an equation with a more positive E cell value, so this is our E cell value, reverses a less positive one. So if it's more positive, it reverses a less positive one. And there's information on the textbook for that. So if you wanted to, you could stop the video and read that. Okay, so here is an example. What happens if you put tin and copper together in 2 separate cells and then connect them via a salt bridge? What would the voltage be? How would we work it out? Got to work out the equations. Now, when we write it out, we write tin, then we put a line, and then tin 2 plus. We must make sure we state the symbols, or the state symbols for them, because that's really important in half cells. So we can write those 2 equations out. So the copper, we write the reduced form of each equation with the electrons always on the left. So copper 2 plus 2 electrons makes copper solid, and that has an E cell value of 0.34 volts, and that's related to hydrogen. Okay, so we set hydrogen to be the 0 point, and therefore if we set the copper one next to it, we're going to get plus 0.34 volts. And the tin, okay, if we do the tin one, that is minus 0.14 volts. So it says there, if using the anti-clockwise rule, remember to write the most negative half equation above the more positive one. I'll go over that because I'm not sure that Sean would have done that. It's something that we used to use a lot more, but it's quite a nice way of working out what happens in electrode potentials. So the copper 2 plus and tin 2 plus can't react together at the same time because they're both gaining electrons to become copper or to become tin. So they can't react like that. Okay, the half reaction with the more positive one, which is this one at the top, is going to be reduced. It's going to be reduced. It's going to get rid of electrons. So it's going to add electrons to itself to make copper solid. So this one is going to go in this direction. So let's have a pen. So this one will go in this direction, but the bottom one is forced to go in the other direction. Okay, and so we can see, we can put a little arrow on that one. So we can say that these ones are pushing it this way, and that pushes it that way. Okay, so we can see how that works. So that means the copper goes in the right direction, or the direction that's written, and tin goes in the opposite direction to the one that's written. Okay, so the overall reaction is copper 2 plus plus tin solid makes tin 2 plus plus copper. In other words, the tin, solid tin, is displacing copper ions from their solution to make copper. And that fits with the reactivity series, which you might have a silly mnemonic to remember. Mine is, please send Lord Charles Maclean a clean zebra if the lame horse can't still go. Bit of a dodgy one, that, because I do actually include some non-metals in there, carbon and hydrogen. You might want to have a go at that. You can see if you can work out what that actually means. Excuse me. So the cell voltage is the difference in the values. And this is the left-hand cell, and this is the right-hand cell. So the more positive one is the left-hand side. So left-hand side. And this one is the right-hand side. Okay, so this is the left-hand side, it's going that way. So basically by left-hand side and right-hand side, I mean that you write the value of this one down first and the value of the right-hand side one down second. And if you were drawing the cells in beakers, you would draw them with the copper in this one, so Cu in this one, and you would draw the tin in this one. Now you will do a practical 27 or 26, where you're going to have a look at trying to work see these E cell values in action. Okay, so let's clear a bit of space so we can see that. So just rub those out. Okay, so we can see that we will get a voltage of plus 0.48 volts. Copper plus tin is feasible. The reverse reaction is not. Okay, so let's move on. So here is that series written with the positive at the top. Okay, and I said that quite pointedly because we're going to look at a different way of viewing it in a bit. Okay, so more positive will gain electrons and go to the right. Okay, more negative will lose electrons and go to the left, the opposite way to it's written. Going to left will reverse the sign of the E cell value, so, or the half cell value. Will the following reactions occur? So what I'm going to ask you to do, and I don't understand it, but my symbols have disappeared. Whoops, where's my symbols gone? They've disappeared. Anyway, you should probably stop and have a go now to see if you can work out what the answers to 1, 2, and 3 are. Down here, 1, 2, and 3. Okay, so let's go through those really quickly. So copper 2 plus plus silver. So the copper 2 plus is here. So it's this one here. And it's plus 0.34. And the silver one is up here, Ag plus plus Ag plus, becomes AGS at the top there. Yeah, so let's highlight that there, so that's on there. And it is also this one. No, it's not, it's this one here. Okay, so just get rid of that. Okay. So let's have a look, see what we've got going on. Copper 2 plus. Well, that's copper 2 plus going that way, except that the silver is more positive. The more positive one is going to go that way. And then this one should go that way. So that's opposite to what we want. So that is not going to happen. It's a big no there for that one. Okay. Right, let's have a look at iron and chlorine. So we've got iron. All right, so that's the iron one, because it's the one that's got iron solid in it, because we've got Fe. And then we need chlorine. So chlorine is, oh, that's way up here. So here's the chlorine one. Okay. So in the chlorine one, the chlorine is positive and the iron is negative. So will this happen? Will Cl2 want to go that way? Well, yes, it will, because this is more positive than this. Okay, so this one will go that way. We'll add 2 electrons to the chlorine, turning it into chloride ions, and that one means we'll take the iron and push it back. So we'll do that, okay, with an arrowhead here. So we're going to push it that way. So we will get iron, and we will react it with chlorine, and we'll end up making chloride and making Fe2+. So that one will go. Right, what about the peroxide? So peroxide is here, and that's also a chloride. That's chloride up here. Ah, the chloride is on the wrong side, because this one is more positive. It's going to go that way. It's going to go to the right-hand side. But chloride is on the wrong side, yeah? So we would want to start with chlorine rather than chloride. We haven't got chlorine, we've got chloride. So this one, again, is not going to work. Okay, so we mentioned the anti-clockwise rule. Now, this is something that I was taught, okay? And it's still a nice, valid way of doing it. So let's get our pen sorted. Let's have a pen. Right, so if we take a pen. Now, if I say I look at lithium, okay, lithium's way up here. It's got a minus 3.03. Now, the thing with this is that you might see this sometimes, that the electrode potentials are written with a more negative at the top, okay? So this one is going to be oxidized. It's going to go that way, okay? So it's pretty much not much above lithium. This is why we, one of the reasons why we use lithium. Okay, so we've got lithium up here. And let's put it with, say, let's put it with iron, okay? So here's our iron down here. So the anti-clockwise rule goes like this, okay? We'll take the bottom left one, okay, here, and we'll react it with the top right one, okay? We're moving in what we call the anti-clockwise direction. So we can write Fe2 plus Li, and then that's going to make that this is going to be one of the products, and that is going to be one of the products. Okay, and you can see we're still following this anti-clockwise rule. So that's going to give us, sorry for writing underneath, I've run out of space, so Li plus FeS. Okay, so I haven't put the state symbols in, but what do I need to do that? Well, this is actually needs 2 electrons, so I need to double the lithium, so 2 and 2. And actually that makes sense if you remember, please send Lord Charles McLean a clean zebra if the lame horse can't still go. Lithium is more reactive than iron, and it will react to still or it will displace the ions from their solution. Now what we've got here is minus 3.03, and down here with the iron we've got minus 0.44. So what we need to realize is that the tire one, this one at the top is going to be on the right hand side, okay, and this one is going to be on the left hand side, okay, or left hand side electrode. So we can work out that E cell is going to be equal to, okay, so we've got minus 0.44, okay, which is the more positive, i.e. the least negative, minus, brackets, minus 3.03. Okay. And then if we can do the maths of that, we can do that minus, so we've got so minus point, I want to be able to do this in my head, 4 plus, because that's going to become positive, plus 3.03 is equal to, if I can read my calculator, 2.59. So plus 2.59 volts. Okay, and that is how we could make a battery with lithium and iron. Okay, now normally you can sort of, hopefully you can start to see where this is going. If I want to make batteries and possibly make them rechargeable, I might need to think about what substances could I combine together. This always intrigued me, these lists of electropotentials. Okay, you see that it says the right-hand electrode system at the top here. This always intrigued me, and I was thinking, well, hang on, why can't I make a super battery? Okay, well, I probably could if I combine lithium. Well, there is another page to this which has got fluorine on it, but if I had the nitrate 3 acid system, I've got plus 99 there, so that would give me plus 99 plus that would give me a voltage of plus 4.02, which is quite a decent voltage. Whether these systems could be recharged is a different matter, because you might lose stuff as gas. That's not obviously there in that system. We're losing it with gas. But I can quite easily, well, there's that might be even better if I've got iron 3 plus and iron 2 plus. That's plus 77. So plus 77. Okay, so I'd have plus 77 instead here. So plus 77 plus 3.03. That gives me a voltage of. So if I was to do lithium with this system, I'd end up with a voltage of plus 3.7. 3.80, which is pretty close to the voltage of a standard lithium-ion battery. Okay, so this is where electrochemistry becomes really important. Okay, so now we've got a value for this, and obviously with the value of being plus 3.8 volts or plus 2.59 volts, that's very definitely going to happen. Okay, that will definitely happen. So what we must have for E cell to work, for a reaction to work, is we must have a half equation. One is an oxidation, one is reduction, otherwise it can't work. That's fairly obvious. And the E cell value can be used to predict the feasibility of the redox reaction. And that comes from this equation here, where we've got delta G, which you've come across before, which is the free energy, is minus N, which N is the number of moles, F is the Faraday constant, and E is E cell. Okay, so Faraday constant is this, it's coulombs per mole. Okay, and coulombs is a measure of charge. Okay, so it's the amount of charge per mole of substance, and obviously we've got moles in there in the form of N. E cell is the cell potential, i.e. something like plus 3.8 or plus 2.59 that we saw from the last slide. N is the number of electrons per mole of product. Okay, so that does relate to the fact that lithium is 1 electron, and that obviously has an effect on the battery output. What kind of value must E be for it to be feasible? So any redox reaction with a positive E cell value will work. Therefore, a half equation with a more positive E value reverses a less positive one. And so we need to have a decent difference. So in the end, this sort of summarizes all the links between things that can be used to predict reactions. So we've got the free energy, we've got the equilibrium constant K, and we've got E cell, okay? And we can see previously we've seen that delta G is linked to K, the equilibrium constant, by minus RT log K. We've now just come across this where we've got delta G equals minus NF E cell. And then we can also link E cell to K, because if we rearrange the equation to get E cell by itself, we can substitute for delta G and therefore we can then we can link them all together. Okay, so here are some worked examples. Two redox equilibrium shown below. Okay, so we've got copper and we've got the nitrate ion becoming NO2. Okay, and in this case, they have been listed with the more negative one or the least positive one at the top. Okay, so the copper one is going to go that way, as it shows lower down, and that one's going to go that way. Okay, so that's less positive. It's going to be reversed. This one is going to go in the direction it's written. So we can predict that copper will react with nitrate and H+, so we must have acid in there. Write down the half equations. We can then state that this one's oxidized. It's going from copper to copper 2+, which is the reverse of the actual way we've written out the E cell value. And this one is going in the right direction as written down here. So that's reduction. So we then need to balance up electrons and stuff. Well, actually, this one's only got 1 electron and that one's got 2 electrons. So we need to multiply this one by 2. Then we construct the overall equation where we actually have to get rid of the electrons, and that makes sense. We balanced it, so we get rid of electrons, no electrons left over, and that gives us an overall equation for the reaction. Okay, so limitations. Okay, so we may have a very high positive E cell value, which suggests the reaction is feasible, but there might be a high activation energy, so we get a slow rate. We must have concentration of 1 moles per decimeter cubed. What happens if it becomes more dilute or more concentrated dark matter? And also non-standard conditions will alter E cells. So, when we talk about car battery length, lifespan, and how we charge those car batteries, then they are weather dependent, temperature dependent. So, and that sort of helps to explain why electric cars don't perform quite so well in the cold, and perform a little bit better when it's in sort of nice, warm, standard conditions. So probably 25 is pretty good for them. So actual conditions may be different from what they are. So let's have a look at Le Chatelier's principle as well. What will happen to electrode potential if the concentration of Fe3+ is decreased? Okay, so we've got this half cell. We'd expect the ion to go over to become Fe2+. What would Le Chatelier say if we reduce the concentration of Fe3+? Okay, well, okay, the more electrons there are, the more negative the potential. Okay, so the equilibrium is going to shift to the left because we need to make more Fe3+, because you change the concentration of Fe3+ to make it lower. So it'll also make more electrons, so electron potential becomes more negative. Okay, so there are some questions in your booklets. Okay, so if you can now, hopefully you should be able to, if I can just stop the video, or tell you to stop the video. Let's just get rid of that. Okay, so you should now be able to stop the video, have a go, and then when you're ready, carry on. Okay, so here is an example. So Fe3+ is tin 2+, which contains the correct ions from the list. We would need to do the forwards, i.e. reduced. Okay, so the ion is more positive, so it's going to go in the reduced direction, Fe3+ to Fe2+, and the tin's going to go in the more oxidized, so from 2+ to 4+. And therefore, we've got the reduced minus the oxidized, or left-hand side minus right-hand side, and this would be the right-hand side, and this one being the left-hand side. Okay, so we've got plus 0.77 minus plus 0.15. Put them together, you get plus 0.625. That's pretty positive, so that's pretty feasible. So Fe3+ will be reduced and SN2+ will be oxidized. Fe3+ is a more powerful oxidizing agent than tin 4+. Okay, so right, so page 17, so we've got that one. Right, so we've said that. Okay, right, then there was the second one, Fe3+ and Br-. If you work out the values, it comes to that. Okay, so that one is not feasible. Negative potential difference. Fe3+ is less powerful than bromine. Reverse reaction would be feasible. Fe2+ plus Br2 would give us a feasibility of plus 0.325 volts. Plus 8, yeah, definitely a good one. Okay, so chlorine will be reduced to chloride and iodine iodide will be oxidized to iodine. Cl2 is more powerful oxidizing agent than I2, and we've done that, so we've seen that chlorine will displace iodide. Okay, which is what we've done there. Okay, that one will be positive, but it could take place, but it might not be spontaneous. The difference is quite small. Okay, so it's going to, probably take a while to happen. Okay, and that one can't take place because they were both gaining electrons. Okay, a species of chlorine would oxidize silver to Ag+. Okay, so that one is +74, positive, so feasible. Iron 2+ will be oxidized to iron 3+, and manganate 7 will be reduced to Mn2+. And obviously we've seen that equation before. And iodate, okay, so iodate, we've got +0.65, that works, okay. It may require a catalyst as you've got two negative ions being reacted together, but it should work out on the electrodes on the system. Okay, so yeah, you can see we've got iodate ions and iodide ions on the same side. Okay, so that is it. Okay, so you should obviously have a go at the textbook, make sure you work through the questions, etc. Okay, let's stop that now.